Welcome to AI Paper Slop.
Hey everyone.
This is the YouTube series for you technical folks out there where we summarize the latest AI and tech papers. We are skipping the banter today because we have a massive reality check to get through regarding autonomous AI agents.
Yeah, we're looking at a huge new paper called ASI-Bench. The subtitle is At the Dawn of Artificial Superintelligence, and it's from a massive consortium of researchers. We're talking Tsinghua, MIT, Harvard, just to name a few.
And if you are building agentic systems right now, you need to hear this core finding immediately. The data shows that today's state-of-the-art AI models are incredibly, almost entirely dependent on step-by-step human guidance for scientific research.
Right, which completely challenges a lot of the hype we're seeing right now.
Exactly. So when they evaluated these top-tier agents on ASI-Bench, which is this massive new benchmark for end-to-end autonomous research, the agents score around 51% when you give them the full scientific method and all the implementation steps.
But the moment you strip away that hand-holding, when you just give the agent the research goal and the raw data, that performance plummets to 26%.
And the craziest part is that the bottleneck isn't the model getting distracted, right?
No, not at all. And it's not even a failure to pick the right method. The primary point of failure is operationalization.
Operationalization.
Right. These models, they can identify the correct methodological approach, but they completely lack the ability to turn that method into a working, executable workflow without a human explicitly mapping out the steps.
So in this deep dive into the source material today, we're going to unpack exactly how this 31,000-hour benchmark was built, and we will look at the super counterintuitive reality of why giving an AI partial guidance is actually way more computationally expensive than giving it zero guidance at all.
Yeah, the cost dynamics on this are wild.
They really are. And we'll also look at what this operationalization bottleneck means for the future of agent architectures. But let's set the stage first.
Okay, let's do it.
Because we just established that AI is struggling with autonomous science. But if you are watching the frontier model releases right now, that might sound strange, right? I mean, we see these models acing graduate-level physics exams.
Oh yeah, writing flawless Python scripts.
Exactly. So why do we even need a new benchmark to tell us we haven't reached artificial superintelligence? What is missing from the existing evaluation frameworks?
Well, the gap really lies between static knowledge retrieval and dynamic, unconstrained exploration, because the existing benchmarks, they're mostly designed to test very specific, isolated slices of capability.
Right, like humanity's last exam.
Yeah, exactly. Humanity's last exam, or HLE, it's a fantastic test of frontier academic knowledge, but it's fundamentally a static Q&A format. It's a test.
And then you have things like SWE-Bench and Scicode for coding.
Right, which are excellent. But in those tests, the problem has already been perfectly scoped and bounded by a human engineer. And even Science Agent Bench, that focuses really heavily on contained data analysis.
So they don't capture the whole picture.
No, not at all. Because true artificial superintelligence requires moving entirely beyond mastering existing knowledge. It demands exploring the unknown.
Which is messy.
Super messy. And ASI needs to independently select methods, handle multi-stage interdependent projects end-to-end, and recover from its own errors. If an experiment fails, it has to pivot. And before this paper, no single benchmark captured that entire messy pipeline.
The sheer scale of the effort to capture that pipeline in ASI-Bench is staggering. To give you all a sense of the engineering involved here, the authors spent over 31,000 human hours building this environment.
Yeah, they didn't just scrape the web for this one.
No, they started with over 1,300 candidate research ideas collected from recent scientific literature, and then they brought in over 40 domain experts.
Wow.
And they ran those ideas through 5 rigorous rounds of human review. We're talking 1,100 review assignments and 1,500 sandbox runs.
Just to weed out the bad tasks.
Exactly. To weed out the bad tasks, fix inconsistencies, and most importantly, eliminate any unintended shortcuts where an AI could just guess the answer without doing the work.
Right, because models love to cheat if they can find a shortcut in the evaluation.
They really do. So they whittled it down to 60 project-level tasks across 11 different domains: math, physics, biology, robotics, electrical engineering, earth science, you name it.
And that cross-domain generality is the crucible here. because the benchmark forces the exact same agent model configuration to figure out complex chemical reaction kinetics in one task and then seamlessly pivot to robot manipulation planning in the next.
So they can't just overfit to software engineering logic.
Precisely, it prevents them from just being really good coding assistants.
I want to push back on this idea of what research actually means for an AI, though. Because I think a lot of us in the tech space sometimes conflate solving a really hard math equation with doing actual research.
That's a really good point.
It's like, if current AI is a brilliant undergraduate who can ace a final exam because the syllabus told them exactly what chapters to memorize, but then they freeze up when they have to write an original thesis, ASI-Bench is basically simulating that thesis defense.
Yeah, that's a great way to look at it.
But how do you quantify that? How do you measure that transition from being a knowledge applier to a knowledge creator in a way that is standardized?
Well, this is where the paper introduces a really brilliant mechanic. They call it the guidance gradient.
The guidance gradient.
Right. So instead of a binary pass or fail on a single prompt, the researchers take the exact same scientific project using the exact same underlying data, and they test the agent under 4 distinct levels of human guidance.
They progressively strip away the scaffolding.
Exactly. They categorize these levels as B1 through B4.
This gradient is where the insights really emerge for me. I can break down the first 2 levels because the distinction is crucial if you're doing any kind of prompt engineering.
Yeah, go for it.
So in B1, the agent gets full guidance. It gets the scientific background, the equations, the specific method it needs to use, and the exact step-by-step solver procedure.
It's basically just an implementation task at that point.
Yeah, just write the code for the pipeline we designed for you. But then we move to B2, and the procedural steps vanish. The agent is only given the method name. It's told what method to use, but not how to implement it.
Right.
So B1 is full instructions, B2 is just pointing at the target. What happens when we strip away the rest in B3 and B4?
Okay, so B3 removes all the methodological guidance entirely. The agent only receives the raw data, the research objective, and the required output format.
Wow, so it's completely on its own.
Pretty much.
Yeah.
It has to independently explore the data set, hypothesize what the underlying scientific model is, and choose the correct method to solve it.
And B4?
B4 takes that exact same bare-bones B3 prompt, data and goal only, but injects factually correct yet task-irrelevant information to act as a distractor.
Let's ground this in a specific example from the paper, just so you can all visualize exactly what the model is seeing in its context window.
Good idea.
The authors detail a task called 2D anisotropic stiff dynamics. In B1, the agent is handed a highly specific prompt. It's told it's looking at a conserved anisotropic Kuramoto-Sivashinsky type equation.
Let's pause on that jargon for just a second, because we need to contextualize the difficulty here.
Yeah, it's a mouthful.
The Kuramoto-Sivashinsky equation is a highly complex mathematical model used to study chaotic systems. We're talking flame fronts, fluid turbulence, things like that.
So this is not basic algebra.
No, this is hardcore graduate-level spatial temporal dynamics.
Okay, perfect context. So in B1, the AI is given the exact mathematical formula for that chaotic system. It's explicitly told to use a 2D Fourier pseudospectral method, and it's even given a warning like, hey, the system is stiff, so use the ETDRK4 time integration method.
It literally just has to write the script.
Exactly. But in B2, the prompt changes completely. It just says this is a stiff fourth-order PDE. ETD methods are reasonable.
It points at the target but hides the map.
Exactly.
Yeah.
And then in B3, the environment becomes completely ruthless.
Yeah. In B3, the agent just gets spatial temporal data arrays. The prompt basically just says, here's a 2D nonlinear system, explore the data, characterize the dynamics, and predict the future field.
No mention of Kuramoto-Sivashinsky at all.
None. No mention of Fourier methods, no mention of ETDRK4.
And B4 just adds noise to that baseline.
Right. They feed the agent that same B3 prompt, but they add distracting notes. Like they'll say, hey, several unrelated PDE families can produce these patterns. Maybe it's a Cahn-Hilliard phase field.
Just to throw it off track.
Exactly. They even throw in background chatter about completely unrelated topics like sports statistics in semiconductor markets.
Wait, really? Sports statistics?
Yeah, purely to test the limits of the model's attention mechanism.
It's essentially a high-stakes cooking competition.
Oh, I like that analogy.
Yeah, so B1 is a precise recipe for a complex souffle, down to the exact gram of flour. B2 is the judge saying, make a souffle. You know what you have to make, but you have to remember the steps.
Right.
B3 is walking into a kitchen with a pile of raw ingredients, and the judge just says, bake something impressive. and B4 is B3, but there's a television blaring a documentary about sushi in the background while you're trying to figure out eggs and flour.
And the results of that cooking challenge, they really expose a massive structural vulnerability in how these foundation models are processing constraints.
So let's look at the actual numbers. When the top 18 state-of-the-art configurations run this gauntlet, we're talking frontier models here, Claude Opus 5, GPT 5.6 Solus, DeepSeek V4 Flash.
The heavy hitters.
Yeah, running inside agent harnesses like Codex and Claude Code. The macro averages across the 60 tasks are a huge wake-up call.
What were the final numbers?
For B1, the step-by-step recipe, the average score is 50.91%.
Okay, not terrible.
But when you step down to B2, where they only get the method name, the score sharply drops to 29.10%.
Wow.
That is a nearly 22-point cliff just from removing the procedural steps.
Yeah.
And moving to B3, no method, just goal and data, it barely drops any further. It lands at 26.62%.
And what about B4 with all the distractions?
B4 actually holds steady at 26.99%.
See, those numbers isolate the exact failure point in the architecture of modern AI. That massive drop between B1 and B2 is the most telling metric in the entire study.
Why is that drop specifically so important?
Because in both of those scenarios, the AI knows exactly what method it needs to use. In B1, it gets the steps. In B2, it has to construct the steps itself. So this proves the core bottleneck holding back autonomous research is method operationalization.
The AI understands the method conceptually, but it can't execute it.
Exactly. It simply cannot translate that concept into a reliable, executable workflow without intense human guidance mapping out the steps.
Which completely inverts our assumptions about what AI is bad at, right? You would naturally assume the hardest part of science is the B2 to B3 jump.
The discovery phase.
Right. You'd think the bottleneck is having the intuition to look at raw data and say, I need to use an ETD method. But the drop from B2 to B3 is tiny. It's only 2.48 points.
Method selection isn't the problem at all.
And the attention mechanisms are also incredibly robust, because the score slightly ticked up in B4 compared to B3.
26.99 versus 26.62, right?
Yeah, which shows these models don't fail because they get distracted by irrelevant information. Context window bloat isn't disrupting their logic. They can tune out the noise about sports and semiconductors perfectly well.
The failure is purely in the execution of multi-step logic.
Which brings us to what I think is the most counterintuitive, almost paradoxical finding in the entire paper. Let's talk about computational costs.
Oh, this is the part that will drive engineers crazy.
Seriously. Because if you're an engineer managing an API budget, you would assume that B3, where the agent has zero guidance and has to figure out everything from scratch, would be the most expensive setting.
You'd expect it to burn through the most tokens and take the longest time, right?
Exactly. But B3 isn't the most expensive. B2 is. How does giving an AI some guidance cost more than giving it no guidance?
We're seeing a quantifiable measurement of severe thrashing. Let's look at the token consumption. B1 averages 4.4 million tokens and about 38 minutes of execution time.
Okay, baseline.
Right. B3 uses 5.4 million tokens and takes 36 minutes. But B2, providing the method name but no steps, consumes 6.9 million tokens.
Wait, 6.9 million.
Yeah, and it takes nearly 50 minutes. That means B2 uses 59% more tokens than B1.
So incomplete guidance introduces massive computational overhead. Why does the model thrash so badly?
It really comes down to how large language models process constraints. In B2, the agent is heavily constrained by a prescribed direction. It knows it must use a specific method because you told it to.
But it doesn't have the steps in its training weights to actually implement it.
Exactly. So it gets trapped. It enters these massive iterative loops, burning compute, as it frantically tries to reconstruct the missing steps to satisfy your constraint.
Wow.
Whereas in B3, because the agent is totally unconstrained, if a method isn't working, it just abandons it. It can easily pivot to a simpler neural surrogate or a completely different approach.
So in B2, you've essentially handed the model a mandate without a manual, and it crashes its own context window, repeatedly failing to compile the exact workflow you demanded.
That is exactly what is happening.
It's exactly like giving a junior developer a Jira ticket that says, implement a custom Redis caching layer, but giving them zero documentation.
Oh man, every engineering manager listening just felt that.
Right. Because they feel forced to use Redis, they're going to spend 3 days thrashing, downloading random libraries, rewriting configs, breaking the build. But if you just gave them the B3 prompt, like make the database queries faster. They might just add a simple index in 10 minutes and close the ticket.
That is a perfect analogy. Complete human guidance sharply reduces search cost. But partial human guidance traps the agent in a highly constrained search space where it lacks the operational skills to navigate.
And the token data proves that perfectly. You aren't simplifying the research by giving the AI a hint. You are just trapping it in a corner.
Yep, pretty much.
Okay, so we just saw how incomplete guidance breaks the model's ability to execute. But that raises a bigger systems architecture question. Is the failure coming from the model's brain? Or is it the software scaffolding, the agent harness, that's failing to manage the workflow?
This is a crucial distinction.
Which systems actually survived this benchmark? Because a lot of you listening are probably wondering which API and framework you should be integrating into your own workflows.
The absolute winner on the benchmark was the Codex harness paired with the GPT 5.6 Sol Ultra model. It was the only system to break the 50% barrier on the brutal B3 setting.
Scoring 51.60%.
Right, and stepping down to just the eye-reasoning level of that exact same model dropped the score by nearly 11 points.
But the paper proves that scientific capability doesn't just emerge from the foundation model alone. The agent harness matters immensely. It's managing the tool use, the file editing, the iterative loops.
Yeah, the harness fundamentally shapes the capability ceiling of the underlying model. The delta in performance between harnesses is massive.
Can you give an example for the data?
Sure. The researchers paired identical models with different harnesses to isolate this. Take the MIMO v2.5 Pro model. When they executed it using its native MIMO code harness, it scored a dismal 16.17 on B3.
Yikes.
But when they unplugged that exact same model and routed it through the Claude code harness, its performance jumped to 23.25.
That is a huge leap just from changing the framework around the model.
Right. And the Kimi K2.7 model showed the same pattern. It jumped from 19.72 using the Kimi code harness to 27.34 using Claude code.
It emphasizes that the foundation model is just the brain in a jar. The harness is the actual pair of hands doing the lab work.
Exactly.
But let me challenge this from a purely pragmatic engineering perspective. If the model matters and the harness matters, and scaling the reasoning compute pushes the score up, couldn't we just conclude that the problem is solvable through brute force?
Ah, the classic scaling argument.
Yeah. Like if we just throw more money, more tokens, and better agent harnesses at the problem, won't we eventually achieve artificial superintelligence and hit 100% on ASI-Bench?
The cost analysis in the paper strongly refutes the brute force approach. Higher cost does not guarantee better performance, and for anyone designing automated systems, this trade-off is brutal.
Let's look at the numbers.
Okay. Compare two specific setups from the data. If you use Codex with GPT 5.6 High, you achieve roughly 41% on B3. The cost for that run is about $684.
Which is already pretty steep for one run.
Right. Now, if you switch to Claude Opus 5 with Claude Code, you get an almost identical score, 40.7%. But the cost per run is a staggering $2,728.
It costs almost exactly 4 times as much for the exact same scientific performance.
Exactly 4 times as much. And while the top performer, GPT 5.6 Ultra, does achieve that 51% win, it costs $1,550 per run.
So if you are an enterprise trying to automate 1,000 data science experiments, you cannot blindly throw compute at the problem.
No, absolutely not. The scaling laws that worked so well for knowledge compression during pre-training, they do not apply linearly to autonomous execution.
Throwing a massively expensive model at a B2 or B3 task often just results in a much more expensive version of thrashing. You end up paying $2,000 for the agent to fail instead of $600.
That's the painful reality of it.
So we've covered the immense scale of this new benchmark. We've dissected the brutal reality of the operationalization bottleneck, explored the B2 thrashing paradox, and mapped out these wild cost dynamics. What is the ultimate takeaway for the AI community?
Well, first, the authors make it clear that ASI-Bench is not meant to be a static test.
Right.
They are actively inviting the scientific and AI communities to contribute new tasks. They have a portal online, and they want researchers to submit problems that define the very frontier of their specific disciplines.
Because the goalposts have to keep moving as the models get better.
Exactly. That community evolution is vital. Because if the industry just over-optimizes for these initial 60 tasks, we will end up with the same illusion of progress we've seen on older benchmarks. The benchmark has to evolve at the same pace as the systems themselves.
That makes total sense. I want to leave you all with a final provocative thought to mull over as you go back to building and testing your own systems. We spent so much time in this industry celebrating when an AI model aces a perfectly structured exam, or when it flawlessly executes a well-documented coding task.
We really do.
But if the defining characteristic of true artificial superintelligence is the ability to independently discover things humans haven't even thought of yet, are we focusing too much of our engineering effort on scaling models that are essentially just really, really good at following instructions?
It's a fundamental question.
Perhaps the true path to ASI isn't about giving models more data to compress or larger context windows to read our detailed recipes.
Yeah.
Perhaps it's about teaching them how to survive the silence when humans stop giving them the steps.
Yeah.
To figure out what to do in the kitchen when the recipe book is thrown out, and it's just them, the raw ingredients, and a goal. Thank you for joining this deep dive into the source material. Until next time, keep questioning the benchmarks.